The next team, the last team in this section, has prompted me to request that the mechanical engineering department has a senior design project next year to make a portable, low-cost document burner. So, this is team number 2, an algorithmic Deshredder, customer Professor Trachtenberg.
Okay, well, good afternoon, everyone. So, basically, back in 1979, the American embassy in Tehran was taken over. At that point in time, there were a lot of sensitive documents that needed to be removed, basically, so that the Iranians couldn't get control of them. Paper shredders were used when the document burner broke, and the Iranians basically put hundreds of thousands of man-hours into reconstructing these documents. So it was a very, very lengthy process, hiring a lot of unskilled labor to be able to put them back together. So basically, though, now with modern computing, that might not necessarily be what you need to put together these documents in a sensitive manner. So that's kind of our goal as a team. So I'm Ryan Norton. We have Richard Tia, Samir Ahmed, Jeff Crowell, and Jacob Moisan in our group. We're team 2 called Algorithmics. Pretty much our objective is to create a software package that can reconstruct shredded documents, because we're really looking into what the vulnerabilities of that encryption system, in this case, shredding a document, could be. So the main motivation came from the DARPA shredding challenge in 2011 that Professor Trachtenberg had seen. And so a lot of those solutions that they came up with during this 2011 challenge came with a lot of user feedback, that you'd use a software package in conjunction with users verifying the data. So our point was really to determine a autonomous software package that all you did is scanned in these shreds, and it'll put them back together again without any user input. So our deliverables then is that desktop application I talked about, that you can install it onto your computer, input scans shreds, and it'll put it together for you. Kind of the more important meat of it, though, is the software algorithm behind it that can then be used open source, that everyone can have access to this code. So here, Jeff will start talking a little bit more about our technical aspect.
Okay, so in order to have this package, we need to first define what we need for inputs. So for specifications, we decided on a single-side, single page of paper. We're currently unable to do multiple pages at once for a double-sided document. A typed document in the English language with 11-point black font on white letter paper. And we've been using a 400 dpi scanner. And the most important qualification is that the shreds are isolated when they're scanned against the high contrast background. And you'll see that in the next slide. So this is an example of one of the documents that we've shredded and scanned. You can see that all of the shreds are separated, so there's definitely some space between each one of these, and they're against this pink high contrast background. One example of an area where we have trouble is, you can see on the edge here, this is what we treat as one shred, but it's actually supposed to be two decided by the shredder. But the two pieces are still somewhat connected, and that's one of the challenges that we faced. So the first step is taking the background, where we scan over the scan and decide which one of these colors represents the background. So in order to do that, we've gone over the edge of the paper and decided that the most common color along that would be the background, and that's usually very successful. The next step is to perform a flood fill around that background color. And we choose a space which is that color, and because the shreds are all separated, performing a flood fill with a given intensity will cover the entire document. The next is to make a mask of that flood fill area, and then finally extract the piece of paper, extract the single shred, and then orient it vertically so that all of the pieces are oriented in the same manner.
So after the pre-processing stage, we move on to the analysis and reconstruction phase. In In terms of analysis, what we want to do is where we want to actually measure, we want to build a metric for similarity of two shreds. So if we have two shreds, how similar are they to each other? First thing we do is we look at the shred, and we look right along the edge, we look at the colors and the luminosity along the edge. We can plot that based on its how dark it is. In this example, you can see whenever you have a little line across the edge, you get a peak, or in this case, not a valley. Then we can try to detect features from that by doing some tricks like convolution, and then look at the, and then we have, basically we get a vector of wherever we have features and the distance from any point to a feature. We can use that vector to compare two shreds to each other. We also have to consider that we have two different sizes of shreds to be compared. So when we compare the shreds, we take every single shred we have, and we compare it to every single other shred. This is actually a little more complicated than it sounds, because we have to take every shred, flip it upside down, and then compare it to every shred, and left and right. Since we're assuming that we're using a standard shredder that doesn't do cross-shredding, we assume we have vertical strips, so those can be put together, and so we have really only two orientations, upside down or right side up. After the analysis phase, we move on to the reconstruction phase, and this is where the core of the algorithm is. What we use a variation of what's called the minimum spanning tree algorithm. So if you can imagine our problem as shreds being vertices in a graph and edges as your similarity between two shreds, what you really want to do is find the minimum spanning tree between all the edges. So you want to repeatedly select the best matches of shreds you can get, and then cluster these shreds together until you have a reconstructed document. There are some differences, like you can only put each shred can only be connected to two other shreds at most, or one shred if it's on that side. So there are some differences. So I'll walk you through a basic high-level view of what we do. We have our difference matrix, or similarity matrix, whichever one. We have unclustered shreds, and what we would do is we would ask our distance matrix, which shreds are the two most similar. It would give us those two, and we put them right next to each other. We would also create a binary tree representation, which is an abstraction that we can use to help manipulate the shreds and see how every join and every decision was being made. So we'll pick that, and we remove those two from our unclustered shreds, put them in the clustered shred category. Repeat the process, taking the next smallest one, and we have another set of shreds, but these two are independent. There's no correlation between them. They're not touching each other as far as we got them. But we keep doing this, pick another one. Eventually, you'll cluster shreds onto other clusters, so you'll have a binary tree, and you'll have another shred you want to add to it, and so that's kind of what we have here. We added a third shred to the left, and we got we added to our tree. So we can move to the output.
So the final output stage is we decide to measure our accuracy as the correct number of edge pairs over the total number of edge pairs. So in the case of 3 shreds, if we got one edge pair correct, that would be 50% accuracy. If we have 2 pairs, one of which is correct. So an artificially created documents, which are documents that we shredded using a digital means by creating an image and then chopping it on like a paint program or using a digital shredder that was written, will give us close to 100% accuracy in reconstructing. For actual documents, we were given slightly less satisfactory results with approximately 50% accuracy in the reconstructions. So for some documents, such as like a W2 form, we were given almost 80% accuracy, and for other documents, such as like the type pages of the book, the accuracy was significantly worse at something like 30%. So here's an example of one form that was very successful in reconstructing. As you can see, from the tax form, have the social security number, some warning, and it's very successful.
So we're also going to talk about the engineering effort behind this, because it took a lot of effort to write code, to test the code, and to write code to make sure what we had was right. So one of the things we wrote that's in the final desktop application is a visualizer. And the visualizer represents all the decisions that were made in building the binary tree that was the full reconstructed document. And so every two shreds are, every shred is a leaf of this tree, and then you can see the percentage confidence it had every time it clustered any two shreds together. You can also look at the match on the right-hand side. We also wrote a feedback tool so that we can automate the process. We can make tweaks, we can change some parameters and see if that led to better reconstruction of documents, and we use that to optimize some parameters that we had. Another thing we did is we wrote a test manager so that it's a pretty tedious process to go shred paper, collect it, and reassemble it ourselves and make sure that they're in the right things, and then scan that, and then test that our digital reconstruction is correct. So we had 600 megabytes worth of shreds. It's going to cost 9 computers that we could use to run unit tests on, and that really improved our development process. We also, Jacob wrote an artificial shredder that we used in the beginning because it really streamlines the testing process, but you might notice that the noise is much less than, this is an artificially shredded document, so we did that. We took an image of a scan and we shredded it on a computer, but it doesn't have the same kind of noise and curvature and things that we had from real shredded scans.
So some of the successes that we had for the pre-processing were background detection, masking, image filling, and extraction. And this was fairly straightforward because using the high contrast background paper, we were able to easily detect the background color, and that lends itself to the next few steps. One of the harder parts was that, as Jeff mentioned earlier, shred separation. So sometimes when we would shred a piece of paper, some of the shreds would be stuck together, and that would cause us to have to compare a straight edge side to a more curved one, and that led to lower results in our final reconstruction. If we had more time for the pre-processing, we would try to fix some of these changes, some of these problems with, for example, shred straightening. When laying down these shreds and gluing them onto the high contrast piece of paper, there's a lot of human error involved. You can't always glue it perfectly straight, and that causes a lot of curvature in the shreds as well. So that's one thing that we would try to improve. For analysis, we had a lot of success with the luminosity matching. That provided us the highest reconstruction rate out of all the other metrics that we tried. And empty shred detection was did pretty well too. We were able to eliminate some of our search space by getting rid of the all-white pieces, so that we only had to compare shreds that actually had information on them. Some things that were ineffective that we did try were OCR-based shred reconstruction, because a lot of the shreds, they were cut on the sides and text was cut in half. So the OCR was trying to recognize full characters, but it was unable to do that. And another metric that we tried along with luminosity was Jacquard or Hamming distance. So we went along the edge of the shreds row by row and built a data structure of whether each row was black-white containing text or not, and that actually lowered our reconstruction percentage as well. And shred normalization was something that we tried to implement to fix the curvature problem that we had, because a lot of our data structures were of different sizes containing the luminosity metric. So we tried to normalize these data structures to the same length, so when comparing them, they would be more similar. So in the future, if we had more time, we would try to implement a partial character OCR so that we could look along each side of the shred, and if we see a group of letters that we see are the left side of the letters, we can look at another shred and we'll say, oh, we see all these, the right side of these letters on another shred. For reconstruction, the Crowell's algorithm that we chose we thought was very good, because we were able to get 80% correct reconstruction on the authentic shreds, whereas we got 100% reconstruction percentages most of the time for the artificial shreds done with Jacob's artificial shredder. So some things that we felt were ineffective were that we used a greedy algorithm. So we would choose the best local match every time, which doesn't necessarily guarantee the best optimal solution in the end. And we were getting as low as 30% reconstruction. Some of the future improvements that we can make to the reconstruction would be backtracking algorithm along with the greedy algorithm, so that we can incrementally evaluate multiple paths as we make our match pairings, and then choose the best ones from that. And another thing would be trigram word clustering. So once we're able to do reconstructions on the word level, we'll be able to determine probabilities for groups of words that are together. So for example, you would expect going to San Francisco instead of going to San York. And another thing would be machine learning, which would involve lots and lots of test data. If we were able to train our algorithm to detect whether or not a shred pairing was good or not, from all of the test data that we had, we figured that that would be a very large improvement in our reconstruction rate.
Alright, so we're going to open source the project. So if anyone wants to view the code base, just go to github.com/algorithmics. You can build upon it on your own. This is our schedule for when we did the most pushes to GitHub. You can see our sleep cycle. Some of the tools we use, OpenCV, we used at MU. Someone else used that earlier today. It's OpenCV wrapper for C#. HTML5 is used for the visualizing tool. JForge, another image processing library for C#. Tesseract was the OCR library we use. GitHub for source control. Microsoft.NET, platform we worked on, and Google Drive and Dropbox for all our syncing of all of our test material. These are the people that assisted us along the way. Professor Kia and Pisano, for directing senior design, Professor Trachtenberg and Conrad for giving us direction along the way, and Professor Trachtenberg for being the customer to make this project possible.
You guys have any questions?
So, did you guys look into which part of the, which problems you ran into, which basically gave you what were the bottlenecks in your algorithm? What caused the biggest problems?
The biggest problems are definitely caused by bad matching metrics. So we had luminosity, which was one way of gauging similarity, but it's not the best way. Or if we had multiple ways that we could factor things in, that would have worked out better. But, I guess it's proof from the artificial cases where we could draw something in paint and then chop it up digitally and reconstruct it perfectly. That proves that our algorithm works if it's given, if what we tell it is a good match, it's a good match. So it's, I guess, an image processing problem. Chris Conrad?
In your performance measurements, you try to assemble only one single document at a time.
Right.
You didn't mix up several documents.
No, we didn't mix up several documents. We know that's unrealistic, but it would be hard to.
I just wanted to make sure.
Yeah. Patrick?
You said you had feedback to kind of shuffle things. Is that in the form of like if I look at a document and it's not working, I can say try again, or do you have to actually go and tweak those yourself?
So the feedback tool that we wrote, and I didn't go into detail, so it's a good question. We would have the scans, the shreds put in the correct order, and then we would digitally shuffle them up, and then try to reconstruct it, and then we could do that process repeatedly. So we would know what the end result should be because it's based on how we put the shreds in. But then we assume that after it's shuffled, it's a different order, and we try to reconstruct it. And it just gave us feedback, so we could make changes, and we could run it, and we could see that our accuracy improved or got worse. That's Trachtenberg.
Yeah, when you said you had 80% accuracy, what does that mean? Does that mean 80% of the time you fully reconstructed the document, or you have some sort of metric on how close it was?
The metric is decided by the number of correct pairings. So on
So it's a timing metric.
80% of the edges were correct, correctly identified.
80% of the edges. Ah, okay. Okay.
Do you guys have any idea like how many shredders are line shredders versus confetti shredders now?
All the shredders that we've seen at BU are line shredders. But it's true that if you really took security as a consideration, you would probably use a cross shredder or something like spiral shreds. So it's definitely considered the weakest form of shredding.
How did the algorithm you settled on your best matches compare to what was the results of the darker challenge?
So the darker challenge didn't have straight shreds. I guess most of them were cross shreds. So we couldn't do an actual comparison versus the material that they put out. But no one, the people who did publish on it all used human interaction to verify. So their algorithm wouldn't do a full reconstruction. It would just give possible matches, and then the human would verify that this is a good match, this is a good match, and then it would cluster based on that. And there was no particular.
Published a date based a lot on the analysis.
Yeah, we took that from leverage.
I understand that you used documents from different shredders, right? Only one single shredder.
We sampled 3 different shredders, 2 in the ECE department and 1 in Eagles.
Because I'm curious whether, for example, edge of a shredder, the blades get dull, and the edges are ripped and not really cleanly cut. But actually this doesn't make it even more difficult.
Yeah, it would make the problem more difficult, and we found that one of the most difficult issues we had was along the edge of a shred, because we were looking at the luminosity, and along the edge of the shred we found right here that you wouldn't actually, even though text went all the way to the end of the page, depending on whether it was like an older blade or a newer blade, you wouldn't get as crisp a cut, and so you get a little bit of shearing on the side, and so we'd have to, and one shed could have shearing and the other one wouldn't, so we'd have to account for that at some point. Yeah, it was a huge factor in the noise.
Since your algorithm uses luminosity primarily, would this be able to robustly handle images on documents?
Yeah, it actually performs much better when we have more images or lines across the page. And it's just plain paragraphs or blocks of text. A lot of the luminosity signatures look very similar.
I think taking it digitally shredded in and comparing it to obviously the right way to go about it. Did you think of advancing that further and maybe putting Photoshop effects on the edges to maybe put calcium blurs or tears and then comparing your algorithm?
No, we didn't think of improving our digital shredder in that sense, but it would definitely have helped in giving us more material to work with, because that was also a limiting factor because it takes a long time to reconstruct these things by hand.
Question, with scan resolution, does that make a difference?
So we did try with lower and higher scan resolutions, and we found there was no clear difference, and there was no we couldn't conclude that it was better or worse. So we don't think scan resolution played a part because it didn't affect the luminosity aspect. We're still getting the same types of matches.
Similarly, did you try, I know you said 11-point font, try larger fonts, and sooner or later it's going to look
Yeah,
like it, right?
larger fonts, the larger the font, usually the harder it got. It's because you get less information, I guess, from the obvious on the side. We implemented OCR and we tried it, and smaller fonts would definitely work better because OCR would pick up more things, but the cutoff on the letters really destroyed some of the OCR results because they're based off natural language models. Let's try it.
If you were designing a shredder now, based on your experience, how would you design it?
Incinerator. But
assuming that's expensive.
Assuming it's too expensive. Even
power-wise.
Yeah, I guess even a cross-cut shredder, which just cut along 2 axes, wouldn't be enough because I think that's something with more time, more effort. It's something that's definitely solvable by a computer. But I guess spiral shredding or things that compress the pages together at the end of it, or cause more, make it more difficult to separate shreds out, would be a more effective shredder.
What random shredder? Random?
In what way?
Oh, cuts in any way it wants.
Yeah, that was it. Yeah, and the smaller the pieces, the better. Patrick?
Do you have a lower threshold for like if it doesn't match to a certain limit, you say that it's not supposed to be in it, or do you try to match every piece you're given in that document?
So since we use a greedy algorithm, we don't have a lower threshold. We always take the best match we can make at every stage. We tried when we inputted OCR, we did try to have, if the OCR didn't, or like the orientation detected by OCR wasn't a good match, we would not allow certain matches. We found that kind of conflicted with greedy algorithm, it would be better suited for backtrack.
Okay, in our current implementation, you could have a shred from multiple documents. Every shred's from a different document, and it'll still try to put it together. So.
Thank you.